Hello, in this video we're going to look at the other kind of vector multiplication, which is the vector product or cross product. A cross B, which is at first glance very similar looking to the scalar product. It's the magnitude of A times the magnitude of B times the sine of the angle in between them. However, this is a vector, and so it has a direction. And we'll say the direction is given by the right-hand rule. In other words, there's a rule for finding the direction. So looks like the boxes are working a little better for me this time. That's good. So as far as right-hand rule goes, what that means is that A crossed with B is perpendicular to A and it's perpendicular to B. So with vector A and vector B drawn, and let's get these lines out of the way, we'll say A over here, and we'll do B over here. Then the cross product between them has to be perpendicular. So if both of these are in the slide, then that means that A cross B has to either be pointing straight out of the slide right at you or straight into the slide. Those are the only directions that are perpendicular to both vectors. So which one is it? And the right-hand rule is what breaks that tie. So it turns out it's actually going to be out of the slide. So we'll draw a circle with a dot in it to represent a vector coming out of the slide. Sort of like looking at the head of an arrow as it comes straight at you. And so that would be A cross B, and then this angle here is phi, the angle in between. In particular, phi needs to be the smallest angle in between. With the dot product that we talked about in an earlier video, it could have been either the smaller angle or the larger. Both are going to work just fine because of how cosine works. In this case, you'd get a negative if you put it on the other side. It has to be the smallest angle in between. All right, well, what would sine do here? If we do the same kind of trick that we did last time, if we drop down a line perpendicular to vector A, then the length of that dashed line is equal to B times the sine of phi. In other words, what this gives you is the magnitude of A times the magnitude of the part of B that's perpendicular. So this looks for the perpendicular part between the two vectors and multiplies them. It's also, as it turns out, equal to the parallelogram that we would get if we drew lines parallel to A and B. It's that area. As far as physics, our interpretation is going to be more like the part that's perpendicular multiplied, more so than trying to calculate an area with this. We're not going to I can't think of any example where we would calculate an area with it. All right, now what about that right-hand rule? What does it have to do with your right hand? Well, let me pause the video so I can spend forever trying to draw a picture of something that looks kind of like a human hand, and I'll be back in a moment. Okay, so believe it or not, that's about the best I could actually do. So this is the thumb up here, fingers, palm, and then a sleeve. The idea of, and this is your right hand, so the creases in the fingers are like here, and the creases in the palms. Okay, so vector A imagines coming out of your fingers. You pick any finger you want, but we'll do, say, middle finger is vector A. And then vector B launches out of your palm, probably at some angle. They're usually not at 90 degrees to each other, but it's coming out of your palm, in this case out of the slide, but drawn in perspective here. So if you always have vector A with your fingers, vector B coming out of your palm, then your thumb tells you the direction of the cross product. This only works if you use your right hand. If you use your left hand, it's a mirror image, and you get the vector going in the opposite direction. So that's why we call it the right hand rule, because it matches the symmetry of your right hand. All right, so let's look at what happens now with the unit vectors. Let's cross I hat with I hat and see what we get. So I hat crossed with I hat, which, as you might guess, is the same thing as j hat crossed j hat, is the same thing as k hat dot, or crossed with k hat. is equal to the magnitude of one times the magnitude of the other, both are going to be 1, times the sine of the angle in between, 0 degrees, and 1 times 1 times 0 is 0. So if you cross a unit vector with itself, you get 0. If you cross a unit vector with a different unit vector, we would get, in this case, I and j would give us 1 times sine of 90 degrees is equal to 1. Now remember, this is a vector product, so it has to have a direction. Well, what direction does it have? You might guess it's going to be another unit vector, and it is. Let's draw what these look like, and we'll use our right-hand rule. So we have I hat, we have j hat, and we cross them. So imagine you stick your fingers in the direction of I, and here's your palm. J is coming out of your palm, and then your thumb is going to be sticking out of the page. Hey, that's the direction of k hat. So I hat crossed with j hat is equal to k hat. If we switch up the order, if we do j hat crossed with I hat, we get minus k hat. Because we'd stick our fingers in the direction of j hat, our palm in the direction of I hat, and then our thumb would be pointing into the slide. So that would be minus k hat, which is a reminder of what happens if we switch up the direction with a cross product. A cross B is equal to minus B cross A. So cross product doesn't commute. This is the first thing we've seen in this class that doesn't commute. That's probably the only thing we'll see in this class that doesn't commute. What happens is you get a minus sign when you flip it around because of that right-hand rule. Alright, and so here we have a pattern. If we cross a unit vector with itself, we get 0. If we cross a unit vector with a different unit vector, and we go in an order that's quote-unquote right-handed, we get the other unit vector. If we go in the other direction, which would be called left-handed, we get the opposite of the other unit vector. So now we can figure out what we would get in general when we cross two vectors in unit vector notation. So if we take A, cross that with B, let's clean that up. That tells us we have AX I hat plus AY J hat plus AZ K hat, and we want to cross that with BX I hat plus BY J hat plus BZ K hat. Okay, and that's going to give us a bunch of terms. It's going to give us 9 terms. We did this before with the dot product, and we got 9 terms, and it's going to happen again. But we're just going to do this once so we can figure out what the general rule is. So the first term is AX I hat, and we'll cross that with BX I hat. So that gives us AX times BX times I hat crossed with I hat. And if we look at our roll up here, that must be 0. Okay, so then we'll add that to AX times, the next one would be BY I hat cross J hat. That's not 0. That turns out to be K hat. And then we do AX BZ. We get I hat cross K hat. And that turns out to be, well, let's look at our picture up here. So fingers in the direction of I. Turn your hand so that your palm is pointing at K. That's going to give you a minus J hat. For the next row, we'll have AY times BX J hat crossed with I hat, which is going to give us a minus K hat. Then we have AY times BY J hat crossed with J hat is 0. Then we have AY times BZ J hat crossed with K hat, which is equal to I hat. Okay, and maybe we're starting to see a pattern now. You might guess that if we go along the diagonal here, we're going to get all zeros, and the other stuff isn't going to be 0. And that's right. So we have, to finish this off, AZ and BX, K hat cross I hat is J hat, AZ times BY, BY is K hat crossed with J hat is minus I hat, and then finally something that's going to be 0 with K hat crossed with K hat, giving us 0. Okay, so notice that we have a positive I hat and a negative I hat, a positive J hat and a negative J hat, a positive and a negative K hat. Okay, this stuff has to all be symmetric, so that's a check to make sure we didn't make any mistake. It also points out that we're going to have a nice little pattern here. Actually, I should learn my lesson from the last video, huh? Leave a little bit more space so PowerPoint doesn't go crazy when I eventually draw a box. So, A cross B is going to be equal to, let's gather up all the terms that have I hats. So that's equal to AY times BZ, and then we have a minus sign here, so minus AZ times BY times I hat. Okay, notice a pattern. We have an I here. This goes with the X direction, a Y and a Z and a Y. Minus, or subtracted. And that pattern is going to hold for the other ones. So we're going to have AZBX minus AXBZ, J hat, and then finally for K hat we would have AXBY minus AYBX, K hat. Alright, and so that is the cross product for two vectors written in unit vector notation. So let's give that a box. Ta-da! Alright, now let's, it's still kind of ugly. And unfortunately that's what cross products are like. Oh, there's no getting around that. There are some memory aids that we can try to help us remember. So if you've had linear algebra before, and you've seen determinants, that's one way to remember this. If you haven't had linear algebra, you're okay. In fact, this might be a quick way to learn determinants. So A cross B, one way we could represent that is a determinant with I hat, J hat, K hat on top. And then in the next row we have AX, AY, AZ, and in the final row we have BX, BY, and BZ. Okay, and if you calculate a determinant, what you do, or one way to do it, is you say, I want to figure out what term goes with I hat. So I cross out the row and the column that goes with I hat and look at what's left over. Okay, so what's left over is a smaller determinant with an AY, an AZ, a BY, and a BZ, all that times I hat. And that pattern holds, whoa, what was that? I guess I'm still in shape mode. There we go. Anyway, like I was saying, and then we do that for J, we cross out J, so then we would be left with AX on BX, AZ on BZ. And there's going to be a minus sign here, and then the last one has a plus sign. We cross out the last row and column, and we're left with AX, AY, BX, BY. I'll clean that up. X and Y. Okay, so that's another way to represent the cross product, and it gives you exactly the same thing. Like I said, if you have no idea what I just wrote, don't worry about that. If you've had linear algebra, this might look familiar and be a little easier to remember, because we have this nice pattern here to start with. You can also think about a pattern between X, Y, and Z that we have. So you think X to Y, Y to Z, Z to X. It's still in weird mode. I don't know how that happened. Okay. There we go. Let's go back a slide. So with x, y, z, then we have y, z, x, and then z, x, y. And then we always subtract whatever this first term is, and we switch the indices. But every term has to have an x, a y, and a z in it. Okay, and the pattern's always x, y, z. And if you go backwards along the pattern, then you have a minus sign. Okay, now you might wonder, why is that? Well, the reason for that is because x, y, and z form a right-handed coordinate system. They necessarily follow the right-hand rule. If you think about your coordinate system, your x, your y, and your z, you've got x, you've got y. In what direction do you draw z? You draw it in the direction that the cross product tells you to draw it. You draw it according to the right-hand rule. So x and y, x cross y is z. It doesn't have to be that way. You could have a left-handed coordinate system, but that's not the convention we use. We always draw a coordinate system so that z shows up right-handed compared to x and y. Alright, so finally let's look at a quick example using a cross product. In this example, we're going to multiply two vectors, a and b. A will be equal to I hat plus 2j hat minus 3k hat, and b will be equal to 2i hat plus j hat plus k hat, and we want to find the cross product between a and b. By the way, these are the same vectors that I used in the earlier video with the dot product, with the scalar product. Of course, this time we're not going to get a scalar, we're going to get a vector. So the nice thing, the only nice thing really, about using unit vectors to multiply to figure out the cross product is you get the direction for free. You don't have to worry about trying to line up your right hand the correct way. It gives you the direction. Okay, so that's going to tell us, and you might want to refer a couple slides earlier to the general rule, but let's try and leave some space here. So we're going to have a term with an I hat in it, we're going to have a term with a j hat in it, and then we're going to have our last term with k hat. Okay? And then each of these is going to be two numbers minus another two numbers. We just need to fill in what these numbers are. Okay, so with x, we're going to have y and z. So we're going to take the y component and the z component. So that's 2 times 1. And then we subtract from that the z component and the y component. So that's negative 3 and 1 go in there. And then for j, what comes after, or which represents the y direction, what comes after y is z. So we start with z, and then x, and then we go xz. So x is 1. And z is 1. And then finally, for z, we have x and y. So we start with the x, and then the y, minus the y, and then the x. Okay? So for the I hat direction, we're going to have 2 plus 3 I hat. For the y direction, we're going to have negative 6 minus 1 j hat, and then for the z direction we're going to have 1 minus 4 k hat, and so that should be 5 I hat minus 7 j hat minus 3 k hat. That should be our answer. And hey, actually looks like I got it right based on my notes over here. So the tricky thing, of course, is making sure you get your terms in the right order, and practice helps there. The other thing to watch out for is making the silly mistake when you have, like, 3 and 2 and you say, oh, 3 times 2 is 5. You mess the whole thing up. And that's cross products. They are very prone to arithmetic errors, but conceptually they're really just multiplying two vectors together. All right, until next time.